Near-Earth asteroids. We begin with the one you've actually seen do damage, because this isn't hypothetical. On February 15, 2013, a 20-meter rock nobody tracked entered the atmosphere over Chelyabinsk, Russia, and exploded with the force of 30 Hiroshima bombs. Nobody died. Over 1,600 people were injured, mostly by flying glass, because everyone ran to their windows to watch the fireball. Let that sink in. The most dangerous part of that asteroid wasn't the asteroid. It was human curiosity. Here's the scale problem. Chelyabinsk-sized objects, 20 meters across, are estimated to hit Earth roughly once every 60 to 100 years. Most land and oceans are empty land, and nobody notices. Step up to 50 meters Tunguska-scale, and the math changes. In 908, an object that size detonated over Siberia and flattened 80 million trees across 2,150 square kilometers. No crater, no impact, just air pressure and a forest that stopped existing. If that had happened over a city, we would measure the death toll in the hundreds of thousands. But here's the thing about size. Every step upward multiplies the energy, not just the damage radius. A 140-meter asteroid carries enough force to destroy a country. A 1-kilometer asteroid would trigger global consequences, dust in the stratosphere, crop failures, a multi-year cooling event, and a 10-kilometer asteroid is the one that ended the dinosaurs. Chicxulub, 66 million years ago. An object roughly the size of Mount Everest base hit what is now Mexico's Yucatan Peninsula at 20 kilometers per second. The impact released energy equivalent to 10 billion Hiroshima bombs in one moment in one place. It vaporized rock into a global debris cloud, triggered continent-spanning wildfires, and blocked sunlight for years. 3/4 of all species on Earth went extinct, not from the blast, from what came after. Here's the fact that changes everything. We already know exactly where the big ones are. NASA and international partners have now mapped over 95% of near-Earth asteroids a kilometer or larger, and none of them are on a collision course for at least the next century. The real danger isn't the giants anymore. It's the smaller, undetected ones, the Chelyabinsk-class rocks that arrive with zero warning because they're too small and too dark to spot with current surveys until they're already close. Let that sink in. We've solved the extinction level problem through tracking. We have not solved the surprise problem. Consider the numbers side by side. There are an estimated 25,000 near-Earth asteroids larger than 140 meters, and we've currently found and cataloged around 44% of them. There are likely millions of Chelyabinsk-sized objects, 20 meters and under, and we've cataloged a tiny fraction of those because they're simply too small and too dim to reflect enough sunlight for ground-based telescopes to reliably spot until they're days away, sometimes hours. In 2019, an asteroid named 2019 OK, roughly 100 meters across, large enough to level a city, passed within 73,000 kilometers of Earth, closer than some communication satellites, and astronomers only noticed it a day before closest approach. That's not a failure of effort. That's the physics of finding a dark rock against a dark sky, which brings us to the objects that arrive even less predictably than asteroids. Comets. If asteroids are the neighbors we've mapped, comets are the strangers who show up once a century and don't call ahead. Most near-Earth asteroids orbit the sun on relatively short, predictable paths, some completing a loop in under 2 years. Long-period comets are different. They originate in the Oort cloud, a shell of icy bodies far beyond Pluto, up to 2 light years from the sun, and some take millions of years to complete a single orbit. When one finally falls inward, we might get only months, sometimes only weeks, of warning before closest approach. Here's the twist. Comets are also faster. Because they arrive from so much farther out, they fall toward the sun under stronger gravitational acceleration, hitting velocities of 50 to 70 kilometers per second, more than double the typical asteroid impact speed. Kinetic energy scales with velocity squared, so a comet the same size as an asteroid can strike with 4 times the destructive force. Comet Hale-Bopp visible to the naked eye for a record 18 months in 997, was itself harmless, its closest approach still over 100 million miles away. It's a reminder of just how big and how visible these objects can be, and how rarely one actually threatens us. But the math still holds. A kilometer scale long period comet on a genuine collision path would be one of the least predictable, least defendable catastrophes in the entire threat catalog, because by the time we see it clearly, we may not have time to do anything about it. There's a second category worth naming: short period comets, like Halley's, which return every 76 years and are consequently well tracked, well modeled, and about as low risk as a comet can be. The real anxiety belongs entirely to the long period, one time visitors, the ones with no orbital history for astronomers to check against. In 2017, an interstellar object called Oumuamua passed through our solar system entirely, the first confirmed visitor from outside it, moving too fast to be gravitationally bound to the sun at all. It was studied for a few frantic weeks, and it left never to return. It posed no danger, but it proved something unsettling. Objects can arrive from interstellar space itself, not just our own solar neighborhood, with essentially no advance notice at all. Rocks and ice, though, aren't the only things that can hit Earth. Sometimes the sun itself throws a punch. Solar flares and coronal mass ejections. This one won't leave a crater. It'll leave the entire planet in the dark. The sun is a 4.6 billion year old fusion reactor, and every so often its magnetic field snaps like an overwound rubber band. That's a solar flare, a burst of radiation that reaches Earth in about 8 minutes, the same time light takes to get here. Attached to the biggest flares is something worse: a coronal mass ejection, a billion-ton cloud of magnetized plasma hurled outward at up to 3,000 kilometers per second. It takes 1 to 3 days to arrive, and when it hits Earth's magnetic field, it doesn't stay in space. Here's the historical proof. In September 1859, the Carrington Event slammed into Earth's magnetosphere so hard that telegraph systems across Europe and North America failed. Some operators reported their equipment sparking and catching fire. And aurora, usually confined to the poles, were visible as far south as the Caribbean. In 1859, that was a light show with some property damage. Today, it would be catastrophic because we've spent the intervening 165 years wiring our entire civilization to the electromagnetic grid. We got a preview in March 989 when a geomagnetic storm knocked out the entire Hydro-Quebec power grid in 92 seconds, leaving 6 million people without power in freezing temperatures. In July 2012, a Carrington-scale eruption blasted off the sun and crossed Earth's exact orbital position, missing us by about 9 days because Earth simply wasn't there yet. NASA physicists have called it the storm that could have set modern civilization back decades. 9 days. That's how close we've already come without most of the planet ever hearing about it. Here's the fact that should genuinely bother you. Estimates put the odds of a Carrington-scale event hitting Earth directly at around 12% per decade. Not per century, per decade. A direct hit today could destroy transformers that take months or years to manufacture and replace, knocking out power grids, GPS, satellite communications, and banking systems simultaneously across entire continents. And there is no defense against the sun itself, only early warning, currently measured in single-digit days. Here's what makes this threat different from every other entry on this list. It doesn't require a rare cosmic alignment or a once-in-a-neon flyby. The sun produces flares and coronal mass ejections constantly on an 11-year activity cycle, and every cycle brings a fresh chance at a direct hit. Modern infrastructure has never actually experienced a Carrington-scale event. Every engineer, every grid operator, every satellite designer alive today is working from models, not lived experience, which is exactly why agencies like NOAA now run 24-hour space weather forecasting. The same way meteorologists track hurricanes, watching sunspot activity, and issuing geomagnetic storm warnings days in advance. The sun, at least, is a threat we can see coming. What comes next arrives having already crossed the galaxy. Gamma ray bursts. This is the only entry on this list that could sterilize a hemisphere of the planet before you finished reading this sentence. A gamma ray burst is the most energetic electromagnetic event known to physics, produced when a massive star collapses into a black hole or when two neutron stars collide, releasing in seconds more energy than the sun will produce in its entire 10 billion year lifetime. That energy doesn't spread in every direction. It fires out in two narrow, focused beams, like a cosmic lighthouse. And if one of those beams happens to sweep across Earth, the effects are not gradual. Here's the mechanism: a nearby gamma ray burst wouldn't burn the surface. It would blast through the atmosphere and trigger a chemical reaction that strips away the ozone layer, in some models, over 50% of it, in a matter of seconds to minutes. Without ozone, ultraviolet radiation from our own sun would reach the surface at lethal intensity, collapsing photosynthesis in the ocean's phytoplankton, the base of the entire marine food chain. Some researchers have proposed a gamma ray burst as a contributing cause of the Ordovician mass extinction roughly 445 million years ago, when nearly 85% of marine species vanished, one of the 5 largest extinctions in Earth's history. It's a hypothesis, not a settled fact, but the physics behind it checks out disturbingly well. Here's the reassuring part, and it matters. Gamma ray bursts require both extreme proximity, generally within a few thousand light years, and near perfect beam alignment pointed directly at us. No known star capable of producing one sits close enough and aimed correctly enough to be considered a credible near-term threat. The nearest stars that could theoretically produce one are either too far away or, as far as we can tell, not aimed our way at all. It's the most catastrophic entry in this entire list, and also the one you should worry about least, which is a strange kind of comfort. To put the odds in perspective, astrophysicists estimate the chance of a gamma ray burst causing a mass extinction on Earth at roughly once every few hundred million to billion years, and we may have already survived one if the Ordovician hypothesis holds, and simply kept going as a planet, as an ecosystem, without ever knowing what almost happened. The candidates capable of producing one, Wolf-Rayet stars and certain binary systems, are cataloged and monitored, and none of the nearby ones are both close enough and correctly aligned. It's the one item on this list where the science is genuinely terrifying and the odds are genuinely comforting at the same time, without contradiction. But if gamma ray bursts are the threat that's almost certainly not pointed at us, our next entry is the one people worry about for the wrong reasons entirely. Supernova radiation, Betelgeuse. Say the name and someone always asks if it's going to kill us. It isn't. Let's talk about why. Betelgeuse is a red supergiant in the constellation Orion, roughly 700 times the diameter of the sun, and it is going to explode. Not might, will. It's in the final stages of stellar fusion, and sometime in the next 100,000 years, it will collapse and detonate as a supernova, briefly outshining every other star in the night sky, visible in broad daylight for weeks. Here's the number that actually matters. Betelgeuse sits about 650 light years away. The distance at which a supernova becomes genuinely dangerous to a planet's ozone layer and surface radiation levels is generally estimated at around 25 to 50 light years. Betelgeuse is roughly 13 to 26 times farther than that danger threshold. When it detonates, Earth will get a spectacular, harmless light show and nothing more. So why does the fear persist? Because the closest star that's going to explode is a ticking time bomb, makes a better headline than the closest star that's going to explode is comfortably, mathematically fine. Real supernova risk exists historically. A supernova within 25 to 30 light years of Earth could double the planet's background radiation dose and damage the ozone layer badly enough to cause mass extinction. But there are currently no stars close enough to Earth in that danger zone that are also near the end of their fusion lifespan. Betelgeuse isn't one of them, and neither is anything else nearby. It's a genuine, terrifying process, just happening at a safe distance, aimed at nobody on a timeline longer than our species has existed. Compare it to IK Pegasi, a binary star system about 150 light years away, containing a white dwarf that could, in several million years become close enough to a Type Ia supernova progenitor to warrant real caution, still comfortably outside the 25 to 30 light year kill radius, but the closest thing astronomers currently flag as worth long-term tracking. Even that isn't a threat to anyone alive now, or for a very long time after. Distance saves us from stellar violence. But not every threat announces itself with light. Some threats are just gravity, showing up uninvited, rogue planets, and stellar flybys. This is the quietest entry on the list, and possibly the strangest. A rogue planet is a planet with no star. Ejected from its original solar system by gravitational interactions with other planets, it drifts through interstellar space alone, unlit, unanchored, following no orbit around anything. Astronomers estimate there could be billions of them wandering the Milky Way, and by definition, we can't easily see them coming because they emit no light of their own. Here's the scenario that keeps orbital dynamicists up at night. Our solar system's planets stay in stable orbits because the gravitational relationships between them are balanced. Introduce a new mass, a rogue planet, or even a passing star drifting close enough, and that balance can shift. Simulations show that a stellar flyby passing within roughly 1,000 astronomical units, still enormously far by everyday standards, but close on a cosmic scale, could measurably perturb the orbits of the outer planets and destabilize the Oort cloud, flinging a fresh wave of comets toward the inner solar system for millennia afterward. Here's the fact that changes everything about how we think of this threat. This isn't rare on a cosmic timescale. Stars pass within a light year of our sun roughly every few 100,000 years, and a star called Gliese 710 is projected to pass through the outer edge of our solar system in about 1.3 million years, close enough to noticeably disturb the Oort cloud. It won't threaten Earth directly. It doesn't need to. It just needs to nudge a few trillion icy objects loose and let gravity do the rest, one comet, one arrival, centuries or millennia later. There is no defense against this one, and no need for one yet. It operates on timescales so vast that soon means hundreds of thousands of years, a comforting kind of slow. There's a smaller, more immediate cousin of this scenario worth mentioning. Free-floating rogue planets passing much closer, not through our solar system, but near enough to be detected by microlensing surveys, a technique that spots them by the way their gravity briefly bends and brightens the light of a background star. Astronomers have found dozens of these wandering worlds this way, some roughly Earth-sized, most gas giants, all of them adrift, none of them anywhere near us. They're less a threat than a humbling statistic, a reminder that planet doesn't require star, and that isolation is apparently a common condition in this galaxy, not a rare one. It's a reminder that our solar system isn't a sealed room. It's a neighborhood, and eventually something walks by close enough to rearrange the furniture. Which raises an obvious question. Of everything on this list, what can we actually do about any of it? Planetary defense. This is the one entry on the list that isn't a threat. It's the answer. For every other item, humanity has been a passive observer, mapping, calculating, waiting. Asteroids are the one exception, because asteroids are the one threat small enough, close enough, and predictable enough to actually intercept. On September 26, 2022, NASA's DART spacecraft, the Double Asteroid Redirection Test, deliberately slammed into a 160-meter asteroid moonlet called Dimorphos at over 22,000 kilometers per hour. Dimorphos posed zero threat to Earth. It was a target of opportunity, a real-world test of kinetic impact deflection. The result: Dimorphos's orbital period around its parent asteroid shortened by 32 minutes, far exceeding the mission's minimum success threshold of just 73 seconds. Here's why that number matters so much. Deflecting an asteroid doesn't require destroying it, and it doesn't require a dramatic last minute save like the movies. It requires a tiny nudge applied years or decades before a potential impact. Change an asteroid's velocity by a fraction of a percent a decade out, and its position at the moment it would have crossed Earth's path shifts by thousands of kilometers, a clean miss instead of a direct hit. DART proved that physics works exactly the way the models predicted on a real object in real space. This is why the asteroid tracking programs matter as much as the deflection technology. Early warning of years or decades turns an extinction event into a solvable engineering problem. Early warning of days, the Chelyabinsk scenario, turns it into a disaster you can only duck from. The entire planetary defense strategy rests on one variable: how much lead time do we get? For asteroids and comets, thanks to DART and decades of sky surveys, the answer is increasingly enough. DART wasn't the only tool in development. The kinetic impactor approach works well for objects we spot years in advance, but agencies are also researching gravity tractors, spacecraft that would fly alongside a threatening asteroid for months and use nothing but their own gravitational pull to slowly tug it off course. And for worst case scenarios where warning time is short and the object is large, nuclear deflection, using a detonation not to destroy the asteroid but to vaporize surface material asymmetrically and push it sideways. None of these are needed today. NASA's Center for Near Earth Object Studies continuously monitors the sky and currently rates every known object at essentially 0 on the Torino Impact Hazard Scale, the 0 to -10 scale used to communicate risk to the public. 0 means no known object currently poses a credible threat. That number is not a hope. It's a measurement updated continuously by people whose entire job is making sure it stays that way. Which brings us to the part of this video that actually matters most, not the fear, but the ranking. So let's rank them, honestly, by actual risk to you, alive right now. At the bottom of the real danger list, gamma ray bursts and dangerous supernovae. Both are catastrophic in theory and functionally absent as near-term threats because nothing close enough and aimed correctly currently exists. File these under fascinating, not urgent. Above that, rogue planets and stellar flybys. Real, physically inevitable eventually, and operating on timescales of hundreds of thousands to millions of years. Not a threat to you. Arguably not a threat to our species at all, given how slowly it unfolds. Above that, comet impacts. Rare, but faster and less predictable than asteroids, with warning times that could be uncomfortably short. Low probability, genuinely difficult to defend against if the timeline is short. Near the top, large asteroid impacts, Tunguska-scale and above. Low annual probability, but well within the range of will happen again eventually. And increasingly well tracked, well understood, and as of 2022, provably deflectable. And at the actual top of the list, the threat most likely to affect you personally in your lifetime: solar storms. A Carrington-scale event carries roughly a 12% chance per decade. No crater, no fireball, just a possible multi-day blackout of the modern electrical grid across entire continents. It is, by a wide margin, the most probable large-scale cosmic disruption a person alive today is likely to actually experience. Notice what this ranking actually says. It isn't ordered by how dramatic each threat sounds. Gamma ray bursts and supernovae make for the best headlines and sit at the bottom. Solar storms sound almost boring, a blackout, and sit at the top because probability and spectacle are two completely different axes, and the universe has never once cared which one makes better television. Here's the honest picture, and it's the one worth remembering. None of this is a countdown. NASA has mapped the civilization-ending asteroids and found none aimed at us. The genuinely apocalyptic stuff, gamma ray bursts, nearby supernovae, is vanishingly rare and, as far as the evidence shows, nowhere near us. The realistic risks, small asteroids, solar storms, are the ones we're actively watching, actively preparing for, and, in the case of asteroids, have already proven we can deflect. The universe is indifferent to us. It was never trying to hit Earth in the first place. But we've spent the last few decades quietly getting very good at making sure that indifference stays harmless. Not bad for stick figures on a rock.